The second talk in this session is by Oğuzhan Erdem. He received his bachelor from Turkey and his PhD from Middle Eastern Technical University in Ankara in 2012. He is now a research assistant professor. No, not a research, a full assistant. He's currently an assistant professor in Trakya University, and his research interests include computer networking and high-speed packet processing.
My presentation is going to be about IP lookup problem in high-speed routers. We proposed a data structure named clustered linked list forest. So I'm going to present our data structure and its supporting architecture. Here is the outline of my presentation. First of all, I will give brief background information about the IP lookup problem. Then I will explain the existing work, and I will move on to our solution and show our implementation result and conclude my presentation. IP lookup is the very well-known classical problem in computer networking. A routing table is a database that stores the prefixes and metrics associated to that prefixes. In IP lookup, the destination IP address of incoming packets are searched in a routing table to find the longest prefix match. Therefore, the IP lookup problem, also known as the longest prefix matching problem, here the outgoing port of incoming packets are determined based on the longest prefix match. The hardware-based solutions for IP lookup can be categorized into two, the TCAM-based solutions and the SRAM-based solutions. The TCAM-based solutions, we know they are simple and the popular solutions. In TCAM-based solutions, the prefixes are stored in a TCAM and search is performed in a single cycle. They are popular, but on the other hand, they have high power consumption and they have high cost. On the other hand, SRAM has high density and low cost, and they are also used. So the SRAM-based solutions mostly use the tree solutions. So, but in tree-based solutions, multiple memory access are required. Therefore, the pipeline techniques are used in IP lookup. The most common two data structure the most common two tree structure are the binary tree and binary search tree. In a binary tree, the path from the root to any black node corresponds to a prefix in a routing table, and it's a very simple data structure. And on the other hand, in a binary search tree, each node stores prefix values, and there is a sorting requirement. And in order to construct a binary search tree, the different length prefixes has to be converted to the predefined fixed lengths. Therefore, because of such extension and the sorting requirement, they have complex preprocessing and hard incremental updates. IP packet forwarding has been the major bottlenecks for internet infrastructure. There are several metrics. These are the throughput and memory efficiency and the update capability. So we know that the major internet carriers and the ISPs develop deploy 100 gigabit per second network interfaces and links. So a single router has to process a single packet in a 3 nanosecond to catch these rates. On the other hand, we know that the size of the existing routing table is increasing very fast. With this growth rate, it's estimated that in 2015, the size of the core routing tables will be 500 key. Due to the IPv4 address exhaustion, the IPv6 protocol is started to be deployed in the world. IPv6 provides much wider address space. In IPv6, we know the size of the IP address is extended from 32-bit to the 128-bit. Also, that transition is going to have a great effect on that growth of the routing table size. And in hardware solutions, the state-of-the-art designs cannot support large routing tables because of the non-available on-chip memory and the number of I/O pins in FPGA. Also, the last metric is the update capacity. We know that routing table entries are continuously added, removed, and modified. These update operations has to be performed in a timely manner to ensure a stable and reliable lookup. The hardware-based solutions can be categorized into four. The linear pattern search in TCAM, it's the popular one, but they have several drawbacks. They're expensive, they are power-hungry, low density, they have large access time, and need huge priority encoder. And the next group is the hash-based solutions. They are simple and fast, but large number of different hash tables and functions are required for each prefix length. And also the hash collisions are one of the other problem. And the next two group is used with SRAMs. The third group, binary bit traversal in pipeline binary tries. They have good throughput performance and support quick prefix updates. However, they suffer from the inefficient memory usage. And the last group, binary value search in pipeline binary search trees. They have good memory performance, but because of prefix extension and the sorting requirements, they have complex pre-processing and update. Now, as an alternative to those groups, we propose to use hierarchical structures for IP lookup. Actually, these structures are used for packet classification. In packet classification, the incoming packets are classified into flows based on the header fields in a filters. So, for instance, hierarchical trie in packet classification is composed of hierarchically connected binary tries. In that structure, there is one big source address trie in the first stage, and there is multiple the destination address tries in the second stage. Sort starts from the first stage, from the source address trie, and when there is a match, sort jumps to the dA trie in the second stage. Even there is a match in the second stage, search has to backtrack to the first stage to search for the other matches to find the highest priority one. Because of that backtracking problem, the hardware implementation of hierarchical structures are unfeasible. In our work, we propose to use hierarchical structures for IP lookup. In our case, we only have destination address, but we can split the prefixes into two parts and represent them by using hierarchically connected data structures. And by using that structure, we can achieve substantial memory saving because bit strings are shared by multiple prefixes, are stored only one time. And in our case, there is no backtracking problem because we use fixed size strings in the first stage, which are naturally pairwise disjoint. In that work, we propose a data structure named clustered linked list forest, and to accommodate that data structure, we propose a linear pipelined SRAM-based architecture on FPGAs. By using a single device, that architecture supports 700 key IPv6 prefixes and a sustained throughput of 432 million lookup per second is achieved. Now, how we construct that clustered linked list forest data structure? Before constructing, each prefix has to be split into two parts, the px part and the py part. Therefore, a single prefix p can be represented as the concatenation of two substrings px and py. Our data structure is composed of two stages. The first stage is the clustering stage. So we use px part in that stage, and the second stage is the linked list stage, and we use py part in that stage. And we also use clustering. What kind of clustering we use? The prefixes can be clustered into groups based on their lengths. So in IPv6, in the worst case, we have 64 clusters. We index each cluster starting from 1 to n. Therefore, Ci represents the ith cluster. However, we can reduce the number of such clusters by merging some of those clusters. If we use merging, we have several parameters. The block size parameter that shows the number of distinct lengths involved in a cluster. So each distinct length block of prefixes in a CI is represented by CIL. For instance, if a cluster CI includes the prefixes of lengths from 8 to 11, then block size of that cluster is 4, and a bunch of prefixes with length 9 can be represented as CI9. The next parameter is the initial prefix right that shows the length of substrings px. For instance, if the IPS value of any cluster is 4, then a prefix p in CI can be represented using two substrings px and py. The length of px is 4. The IPS value is fixed for each cluster. Now, which data structures we use in each stage in our hierarchical structure? Even though any type of data structure can be used, for the first stage, we propose to use binary search tree. Binary search tree is constructed by using the px part of prefixes. In the second stage, we propose to use linked list data structure, so that each node in linked list store the py part of prefixes. Each node of tree connects a linked list data structure in the second stage. Therefore, the number of linked list instances in the second stage depends on the number of nodes in the tree. Here we have a simple clustered linked list forest data structure in the figure by using this simple sample routing table on the left side. We have 3 clusters here. The first cluster, C1, includes prefixes whose lengths are 2 and 3. Therefore, the block size of that cluster is 2. And similarly, the second cluster, C2, includes the prefixes whose lengths are 4 and 5. Therefore, the block size is, again, 2. And the last cluster includes the prefixes whose lengths are longer than 6, and block size is 3. And the IPS value of cluster C1, C2, and C3 are 2, 3, and 4, respectively. The depth of the linked list in the second stage depends on the number of prefixes that share the same px part. For instance, in cluster 2, P11, P8, and P14 has the same px part. Therefore, they are in the same list. Now, let's move on to IP lookup process. It's very simple. In IP lookup, we first split the IP address into 2 parts, IPX part and IPY part. And these parts, the IPX part is sorted in stage 1, and the IPY part is sorted in stage 2. After we obtained these the sub-addresses, these are given to the clusters, and the search is performed in parallel. If there's a match in the first stage in BST node, then we jump to the second stage, the linked list stage. At each node, IPY sub-address is compared with the PY sub-prefix. If there's a match, and if that match is longer than the previous match, the search result is updated. And when all the nodes are traversed, then search terminates. At the end, the outputs are given to the priority encoder that chooses the longest match. We have several optimizations to improve the memory efficiency and also reduce the depth of the data structure. We can categorize these optimizations into 2, the node size optimizations and clustering optimizations. In the first stage, the nodes of these 3 can be enhanced to store PY substrings also. Therefore, we set a limit for the number of PY substrings per 3 node and call P3. And also in the second stage, the linked list nodes can be enhanced to store more than 1 PY part. And we also set a bound, upper bound, for the number of PY prefixes in the linked list node. So by using such optimizations, we can reduce the depth of the data structure, depth of the linked list structure in the second stage. And next, we use clustering optimization. We can play with the BS and IPS values In practical, BS value defines the number and size of clusters. In hardware implementation, the BS defines the number of pipelines, and IPS value determines the number of nodes in BST and LL. We can play with these parameters and to improve the memory. Here is the block diagram of architecture that supports our data structure. Each cluster has two consecutive pipelines. The first one is the binary BST pipeline, and the second one is the linked list pipeline. The binary search tree in the first stage is mapped onto that pipeline. Each level in a tree is mapped onto a unique stage in that pipeline. And similarly, the linked list data structure is mapped onto the LL pipeline. The number of pipelines here depends on the number of clusters, and the number of stages in each pipeline depends on the depth of the data structure used. So we implement that architecture on FPGA platform. On the right side, we see a single stage of these pipelines. Each stage includes a BRAM and the match module. BRAM is used to store the tree nodes and the linked list nodes. Match module compares the IP address with the stored prefix and determines the address of the next node or updates the search result. Since we use dual-ported VRAMs, the architecture is configured as dual linear pipelines. Therefore, the lookup is doubled. Now I'm going to show our implementation results. The 10 IPv core routing tables were used to generate 10 synthetic IPv6 routing tables. That table shows the size of the routing tables, and the figure shows the prefix length distribution. First of all, I'm going to show our memory results. The first two figures show the change of memory requirement based on the PS, IPS, P3, and PLL values. So the table compares the memory requirement of the state-of-the-art algorithms. These candidates are binary trie with path compression, distance-bounded path compression, binary search tree, compact trie-forest, and our data structure. The results confirm that our data structure provides substantial memory saving when compared to the existing solutions. Next, let's see the delay performance. The first figure shows the change of delay for various P3 and PLL values. When we increase PLL, which means when we increase the size of the node, linked list node, in the second stage, the delay drops. And the next figure shows the percentage of memory used by the first stage and the second stage for various IPS values. And also in the top of the figure, we can see the change of delay with respect to the IPS value. When we increase the initial stride value, the size of the tree in the first stage increases, and the delay drops, because when we increase the IPS value, the possibility of sharing bit strings drops. And finally, that table shows the delay for the other experimental IPv6 tables. The delay is in cycles. It's about 45 cycles. Now, finally, our throughput results. We implemented the architecture in Verilog using Xilinx ISE as the target device as Vertex 6. Then our design runs at 216 megahertz and 432 million lookup per second is achieved. That translates into 138 gigabit per second throughput. And that table compares the state-of-the-art architectures in IPv6 with respect to the memory efficiency, the throughput, and throughput efficiency. The memory efficiency is calculated as the ratio of the total memory requirement to the number of prefixes, and the throughput efficiency is calculated as the ratio of the throughput to the memory efficiency. The results prove that our architecture outperforms all the existing solutions in all sites. In this work, we proposed a clustered linked list forest data structure that achieves significant memory saving. and the performance of the design can be improved with several optimizations. And we also propose linear SRAM-based pipelined architecture on FPGAs that achieves that single device that support 700 IPv6 prefixes and can achieve the throughput of 138 gigabits. In a future work, we plan to extend our algorithm to support the virtual routers. Yeah, thank you.
Yeah, so the performance table on your previous slide, where it was talking about the total number of bits that were required, are those for yeah, that's right. Were those for /32 or /128? 32?
Which one?
Okay, it says, there's a column that says memory efficiency bits per prefix.
Okay.
What kind of prefix?
IPv6.
So these are /126 or what type of prefix? Mix?
Here, the number of prefixes is here, we use. Then we divided the total memory requirement to that value and obtained this one.
Okay, thank you.
64, right? IPv6, right?
IPv6, 128 bit.
128. Okay, so that's more questions? I have a question about how easy is it to add new prefixes or remove prefixes from your tables, especially that you map it to a pipeline. Do you have to reconfigure the pipeline, or?
Actually, update is another important metric in such architectures. It's incremental update. There is no reconfiguration, no need to reconfigure the pipeline. We just issue a bubble. Then that bubble traverses the pipeline, stay one by one stage, then write to the BRAM module. There is no hardware change, only the memory change in each stage when we add prefix or delete.
And it doesn't change the balance of the pipeline stages, or?
Yeah, in our case, the pipeline stages are balanced because we use linked list structure. But when you use trie-based solutions, since in the initial levels, the number of nodes are increasing when we go to the depth. But in our structure, it's balanced.
Thank you. Any more questions?
I couldn't hear. Could you please ask?
So my question is, the number of prefixes you're showing are 300 or so. Is it in thousands or just 300 prefixes?
In key. 324 key.
Those are the number of rules, or is it those many thousand rules?
Number of prefixes, thousand.
But does it scale your solution to, as you said, right, number of IPv6 prefixes are of 500K. Does your solution scale to that many rules?
Actually, by using the real IPv4 routing tables, we generated those IPv6 tables. And the mapping is one-to-one. Therefore, in actual, we couldn't find the real IPv6 tables. Therefore, we generated synthetic tables. And here it's shown the prefix length distribution.
I see. So up to you max it to 64 prefix length in that case.
Yeah, we have that number of prefixes.
For each. And is it random? Random generation of the prefixes or any?
Actually, in our paper, we referenced another paper that used non-random generation of IPv6 routing tables. When you read the paper, you can see the reference that generates the IPv6 prefixes by using the IPv4 prefixes.
Okay. Now you choose up to 64. Is it because that's the typical IPv6 prefix length?
Actually,
is this distribution across from 1 to 16 to 64 that you're showing?
Okay, the length of IPv6 prefixes is 128.
Sure.
But the high order of the 64 bits are used for network routing only.
Right.
Therefore, we used such 64 bits.
Right. Now, my question, I understand that part. So my question is, then the distribution that you're showing here, the number of prefixes with the prefix length, is it based on some research, like you looked at some ISP distribution, or is it, how did you, or that's a paper you're referencing?
No, this is just actually, this is the replica of the IPv4 distribution. IPv4, when you divide this distribution into two, then, you know, in IPv4, the half of the prefix are 24 bits length. Therefore, since the mapping is one-to-one, the distribution of prefixes is very similar, almost the same with IPv4 case.
Okay, thank you.